In this example problem, we're in a grocery store and you are pushing a 14.5 kilogram shopping cart with a force of 12 newtons. If the cart starts at rest, how far does it move in 3.00 seconds? So immediately you should recognize that Newton's second law doesn't involve time at all. So this is actually going to be a nice combination of the equations of motion, so the kinematic equations that we've used previously, and Newton's second law. So now we're combining, how we describe motion, that's the kinematic equations, and we're also looking at the cause of the motion using Newton's second law. So in this problem, we're going to start by drawing our free body diagram. So I've already got my picture sketched down below, and we want to start with step one. So sketch all the forces that are acting on this object, and we're going to assume that friction can be ignored. So we're not going to introduce friction for a few sections from now. So here we have this shopping cart, and you're applying a force which we'll assume is perfectly horizontal of 12.0 newtons. So I'll draw the force acting straight to the right, and that is what I'll say is just force F, which is equal to 12.0 newtons. Now, even though there are some other forces in this problem that may not be relevant, we have to draw all the forces. According to step number one, identify and sketch all the forces acting on the object. And since the cart is the object of interest, we want to draw all the forces that are on the cart. So we also know that there's going to be a weight of the cart. So the weight of the cart is going to be acting down, straight down, because it's caused by the force of gravity. And that's going to be W. So we'll call that weight. And we know that the weight is going to be equal to the mass times the acceleration due to gravity. So we can go ahead and fill this in, as 14.5 kilograms for the mass times 9.81 meters per second squared. So 14.5 kilograms times 9.81 meters per second squared. That gives us a weight of approximately 142.245 newtons. And remember, I never round until the very end, so I'm going to leave all of these digits that show up in my calculator. So even though you may be tempted to round at this point, we never round until the very end. Now we know that this cart is not accelerating in the y direction, so there has to be another force pushing up on this cart. So that's going to be the force from the ground on the cart. Which, you may look at this and say, well, there's a force acting up on this wheel and a force acting up on this wheel, but let's not make it too complicated right now. So I'm just going to draw a force acting up, acting up on this cart at the top. We're going to call that the normal force. So we're going to call that N at the top. Now, since this cart is not accelerating in the y direction, we can go ahead and assume that the normal force is equal but opposite to the weight. It's equal but opposite to the weight. So this force must also be equal to 142.245 newtons, but it's going to be acting up. So when I start plugging it into my equation, the normal force, of course, will be positive because it's acting up, and the weight will be negative because it's going down. But let's just hold off on the signs for just a minute. Now, since we're ignoring friction, those are all the forces that are acting on this cart. Then step number two says isolate the object of interest. So we just want to replace the object with a point mass, and we want to apply all the forces that we have on here to that point mass. So I'll go off to the right. We'll say that this is the cart. This one point is the cart. With mass, the mass of the cart is, or the mass of this point is the same as the cart, so it's 14.5 kilograms. Now we want to draw all the forces on this single point. So we have the weight, acting straight down. So the weight we know is 142. So my weight will go straight down. So the weight is equal to 142.245 newtons. We know that there is a normal force, okay, because this point is not accelerating up or down. The normal force is acting straight up. Okay, straight up. So that's the normal force is equal to 142.245 newtons. And we know that you're pushing it to the right, directly to the right. Okay, so F is equal to the 12.0 newtons. Okay, so now we've completed step number 2. Step number 3 says choose a convenient coordinate system. Now we're not making things too complicated here, so let's just use our traditional coordinate system, where up is our positive y-axis and to the right is our positive x. So we have to the right is positive x and up is positive y. Continue on to step number 4. It says break the forces into components. Now, again, this is a very simple problem because my normal force and the weight are parallel to the y-axis. So we don't have to break those into their components because they are equal to the y components. Same for the force that you're applying. It is perfectly horizontal, just like your x-axis. So it's going to be equal to the x component because it's perfectly to the right. Alright, so just making a note of this at the bottom, we know that the normal force, here, let's maybe write this. Well, we're kind of out of room, so let's write this on the next slide. So we go over here, and we have our normal force. Okay, so our normal force, because it is perfectly straight up, we know that the normal force is going to be equal to the y component of the normal force, which is going to be equal to our 142.245. Okay, so 142.245 newtons. And since it's going straight up, okay, the normal force is straight up with my y-axis. According to the coordinate system that we set up here, it needs to be positive. Okay, so that's good. And just for clarity, I'm going to put that the x component of the normal force is 0 in this case. Now, we also know that we have the weight in the y direction. So the weight, okay, the weight that you're given, because it is parallel to the y-axis, we know that's going to be equal to the y component. And since it's acting downward, okay, it's going to be negative 142.245 newtons. And just for clarity, we're going to say that the x component of the weight is going to be equal to 0. Okay. Now we have the force that you're applying. Now keep in mind here that the force that you're applying is in the x direction, not the y. So the force that you're applying, okay, the force that you're applying is equal to the x component of the force, which is equal to 12.0 newtons. And again, for clarity, that means that the y component that you're applying in this case is 0 newtons. So now we've completed step number 4, which says to break the forces into components. Now we just need to do the last step, which is apply Newton's second law to each coordinate direction. So let's look at this problem and see if we can make it a little bit easier. You're looking to see how far the cart moves in the x direction. Okay, so obviously if you're pushing this in the x direction, then it needs to be moving in the x direction because that's the only force that's being applied to the cart. And we want to know how far it moves in 3.0 seconds. So honestly and truly, we don't even need to worry about the y components in this case. I sort of went above and beyond for this example just to get you used to breaking vectors into their x and y components. So the only one that we really need to worry about is the sum of forces. So the sum of forces in the y direction, or I'm sorry, the x direction, and that's going to be equal to the mass times the acceleration in the x direction. Okay, so what this says, okay, left-hand side says add up, so sum up all the forces that we have in the x direction. Well, that should be really easy because we only have one force in the x direction, and that's the force that you're applying. So if I sum up all the forces in the x direction, it's just going to be 12.0 newtons. We know that's going to be equal to the mass of the object that is moving. In this case, okay, that's our point particle, for the cart. So the mass is 14.5 kilograms. So I'll just plug in that 14.5 kilograms. And from this equation, Newton's second law, I can solve for the acceleration in the x direction. So we divide both sides by 14.5 kilograms and divide the left-hand side by 14.5 kilograms. Obviously on the right-hand side, the 14.5's cancel out, and I'm left with the acceleration in the x direction is equal to 12 divided by 14.5. Typing that into my calculator, we get approximately 0.27 meters per second squared. Now I cut it off here. I'm not rounding yet because we still haven't solved this problem. So when I continue my calculations, I'm going to type in 0.82758621, so all the digits that I have in the calculator to keep it exact. Because remember, we don't round until the very end of the problem. Now, at this point, we have the acceleration in the x direction, but what we're looking for is how far the cart travels in 3.0 seconds. So at this point, we need to go back to the equations of motion that we used in the kinematics section and solve for the distance that it travels. So if you look at your equations of motion formula sheet, you can see that we need to use one of our first kinematics. So the kinematic we're going to use in this case is going to be xf is equal to x naught plus v naught x times t plus 1/2 ax t squared. And the reason is because we know what we're working in the x direction. Now, to keep this consistent with the problems that we've done previously, I'm going to go to the next slide, and I'm going to write down everything that we know about this problem in the x direction. So we know in this problem, we know the time is 3 seconds, which is a scalar quantity, so I don't have to worry about breaking it into our x and y components. So I'm just going to write t is equal to 3.00 seconds. Okay, we now know that the acceleration in the x direction is that 0.827 blah 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 blah. So we have the acceleration in the x direction is equal to 0.8227 meters per second squared. And we also know that this cart, so if the cart starts from rest, we know that the initial velocity in the x direction, is also equal to 0. So just like we did on our previous problems, now we need to set up a coordinate system for our cart, so that way we know where our x initial and x final will be. So you guys know that I like to start. Okay, I like to put the origin where the cart begins. So we'll just say that the origin in this case is going to be where the cart begins. So the origin's here, which means that the x naught in this case, so where the cart begins, is going to be 0. So what does this mean? That means if I plug in v naught x is equal to 0, that means that my second term goes away. If I plug in x naught equals 0 into my kinematic, that means that the x naught goes away. And then all that's left is this relatively simple formula to solve for the distance, which is 1/2 ax times t squared. Plugging in my ax that I solved for using Newton's second law, and plugging in my time, which is 3 seconds, I get is equal to 1/2 times 0.827 meters per second squared, okay, times 3.00 seconds. Don't forget to square your time. and plugging that all into my calculator. And don't forget, I'm not plugging in 0.827. I'm plugging in 0.827 blah, 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 because I'm not rounding it until the very end. So we type all of this into the calculator, and we get approximately 3.72 meters. So that is our XF, so the final distance that we travel in the X direction. So what this tells me is, okay, that in 3 seconds of pushing this cart with a force of 12 newtons, okay, the cart travels approximately 3.72 meters. So just to summarize, now that we know how to work with the cause of motion, we're able to use Newton's second law. We solve for the acceleration of the cart, and then we use that acceleration in one of our kinematic equations, and then we solve for the distance that we travel. I hope you enjoyed this problem. If you have any questions, just raise your hand and ask.